Welcome back to another journey through the Boring Space Deep Dive series. Tonight, we're not chasing spectacle or cosmic fireworks. We're settling into something quieter, deeper, a mystery that lives in the space between stars, in the gentle stretching of everything that is. If you're here with dimmed lights, perhaps studying, perhaps drifting towards sleep, you've found the right place. This is a story told slowly, like watching constellations wheel overhead through a long, quiet night. Take a slow breath with me. Tonight, we're exploring why the universe refuses to slow down, not with urgency, but with wonder. Not with answers that close doors, but with questions that open infinite skies. Let the world fade. Let your shoulders drop. We have 2 hours together and nowhere else we need to be. Drift with me into a universe stretching like a quiet sea, carrying every star farther from home. Before we can understand why the universe won't slow its endless race, we need to feel what it means for space itself to grow. Close your eyes for just a moment. Imagine the room around you, the walls, the air between objects. Now, imagine that air itself is stretching, pulling everything gently apart without anything actually moving through space. This is expansion, and it's one of the most beautiful, unsettling truths we've ever discovered. Let's travel back to 1929, to a telescope dome in California, where a man named Edwin Hubble spent his nights doing what we're doing now, staring into the dark, looking for patterns in the cosmic quiet. Hubble wasn't looking for expansion. He was simply measuring light from distant galaxies, collecting photons that had traveled for millions of years to reach his instruments. But in that light, he found something extraordinary. He found motion written in color. You know how an ambulance siren changes pitch as it drives past you? Higher when it approaches, lower as it pulls away. Light does the same thing. When something moves away from us, its light stretches, shifts toward the red end of the spectrum. We call this redshift. Hubble saw that nearly every galaxy he observed was redshifted. Every single one was moving away from us. But here's what made his discovery revolutionary. The farther away a galaxy was, the faster it was receding. Twice as far, twice as fast. 3 times as far, 3 times as fast. Think of it like a balloon being inflated. Draw dots on the balloon's surface with a marker. As you blow air into the balloon, every dot moves away from every other dot, not because the dots are traveling across the rubber, but because the rubber itself is expanding. Space is that rubber. Galaxies are those dots. Or picture baking raisin bread. As the dough rises in the oven, the raisins representing galaxies all move apart from each other. From any single raisin's perspective, all the other raisins appear to be moving away. None of them is at the center. The space between them is simply growing. This was Hubble's gift to us. The universe is not static. It's not a fixed stage on which things happen. The stage itself is growing, carrying everything with it like confetti on an expanding cosmic tide. But if the universe is expanding now, stretching endlessly outward, what does that mean about its past? Run the film backward in your mind. If everything is moving apart now, then yesterday everything was closer together. A year ago, closer still. A million years ago, even closer. Keep rewinding, keep compressing, and eventually you reach a moment when all the space in the universe, all the matter and energy, all the potential for stars and galaxies, and you sitting here listening to these words. All of it was compressed into something unimaginably small and dense and hot. This is what we call the Big Bang. Not an explosion into space, but an explosion of space itself. From that primordial fireball came the hydrogen and helium that would eventually form stars. From those stars came the heavier elements, carbon, oxygen, iron forged in stellar furnaces and scattered across space when those stars died. From those scattered elements came planets, oceans, life. From life came consciousness. From consciousness came the ability to look back and wonder, where did all this come from? Around 13.8 billion years ago, according to measurements from spacecraft like NASA's Wilkinson Microwave Anisotropy Probe and ESA's Planck satellite, our universe began. Not at a point in space, but as space itself. Time began then too. Asking what came before is like asking what's north of the North Pole. The question dissolves because the framework it requires doesn't exist. In those first microseconds, the universe was a sea of pure energy, too hot for atoms to form. Particles and antiparticles flickered in and out of existence. Then, as space expanded and cooled, quarks bound together to form protons and neutrons. After about 3 minutes, these nuclei captured electrons, forming the first simple atoms. For the next 380,000 years, the universe was opaque, a fog of plasma where photons couldn't travel far before being scattered. Then, as temperatures dropped below about 3,000 degrees Kelvin, electrons and nuclei combined permanently. Light could finally travel freely. This moment of first light, what cosmologists call recombination, left behind a glow we can still detect today, stretched by expansion into microwave wavelengths, a faint whisper of the universe's infancy. This cosmic microwave background radiation is like a baby photo of the universe, showing tiny fluctuations in temperature and density that would eventually grow into the galaxies we see today. Think of the universe's expansion like a stone dropped into a still pond. The ripples spread outward in all directions, carrying the impact of that single moment across the water's surface. We are living in those ripples, billions of years after the stone fell. Or imagine a photograph slowly coming into focus in a dark room's chemical bath. At first, just vague shapes and shadows. Then gradually, structures emerge, edges, contrasts, details. The universe developed like that photograph, cooling and expanding, allowing complexity to crystallize from simplicity. Hubble's 1929 discovery gave us the expanding universe, but he didn't know about the Big Bang yet. That understanding came later, built by physicists like Georges Lemaitre, a Belgian priest and scientist who first proposed what he called the primeval atom, the idea that the universe emerged from an incredibly dense, hot beginning. For decades after Hubble's revelation, cosmologists assumed the story was simple. The universe exploded into being, and gravity has been gradually slowing its expansion ever since. Like a ball thrown into the air, rising but inevitably slowing, destined to eventually fall back down or at least to stop rising, frozen at some maximum height. The expansion Hubble measured was seen as an echo of that initial explosion, gradually decaying, gradually losing speed against gravity's relentless pull. But the universe had a surprise waiting. Tonight, we're going to discover together why that simple story expansion slowing under gravity's brake turns out to be beautifully, mysteriously wrong. We're going to feel what it means to live in a cosmos that's not just expanding, but accelerating, racing faster and faster into an unknowable future. Imagine you're standing on a beach at night, watching waves roll in. Each wave seems to come from the same source, the same rhythm. But then you notice something strange. The waves aren't slowing as they approach shore, they're speeding up. Each one arrives faster than the last, defying everything you understand about how water should behave. That's our universe. And the question that will guide us through these 2 hours is simple, profound, and still not fully answered. Why won't the universe slow down? Take a slow breath. Feel your place in this expanding cosmos. You're sitting in a room, on a planet, in a galaxy, carried by a current of space that's been flowing for almost 14 billion years. Every atom in your body was forged in stars that lived and died before our sun was born. You are the universe, looking back at itself. And together, we're going to explore why it refuses to stop running. Feel gravity's gentle pull, trying to gather the cosmos like a fading embrace. There's a profound symmetry to gravity. It's the universe's way of reaching out, of creating connection across empty space. Every particle of matter tugs on every other particle, no matter how distant, gentle, patient, eternal. If you toss a ball into the air, gravity slows it down. The ball rises, but with each moment its upward speed decreases until it stops at the peak of its arc, hangs there for just an instant, weightless, timeless, and then falls back down. This is what early cosmologists expected for the universe. The Big Bang threw everything outward with tremendous force, but gravity should act like cosmic friction, gradually slowing that expansion. Maybe not enough to reverse it, but at least enough to decelerate it over time. Imagine dropping a stone into honey. The stone sinks, but the honey's viscosity resists it, slowing its fall. Gravity should work on the expanding universe like that, not stopping it immediately, but draining its momentum, making each passing eon a little slower than the last. In the decades after Hubble's discovery, physicists worked to understand the universe's fate. Their mathematics was elegant and unforgiving. There were essentially 3 possibilities, each depending on how much matter exists in the cosmos. If there's too much matter, gravity wins completely. The expansion slows, stops, and reverses. Everything that was flung apart in the Big Bang eventually collapses back together in what cosmologists call the Big Crunch, a mirror image of the Big Bang, ending in infinite density and temperature. The universe has a finite lifetime, a complete arc from birth to death. If there's too little matter, gravity loses. The expansion continues forever, gradually slowing but never stopping, like that ball tossed upward with just enough speed to escape Earth's gravity well. The universe expands into eternity, growing ever colder and more dilute, stars burning out one by one until only darkness remains. And if the amount of matter is precisely balanced in what's called a flat or critical universe, the expansion continues forever, but slows towards zero speed, like reaching the top of a hill with exactly 0 velocity. Mathematically perfect, physically improbable. All 3 scenarios shared one fundamental assumption: expansion should be slowing down. This assumption wasn't arbitrary. It came from Einstein's general relativity, the most successful theory of gravity ever conceived. Einstein showed that mass and energy curve space and time, creating what we experience as gravitational attraction. More mass means more curvature, stronger attraction, more resistance to expansion. Think of space as a stretched rubber sheet. Place a heavy ball in the center that's a massive object like a star. The sheet dimples, curves downward. Roll a smaller ball nearby, and it spirals inward, drawn by the curvature. That's gravity, not a force pulling through empty space, but the geometry of space itself responding to mass and energy. When Einstein first applied his equations to the entire universe in 1917, he discovered something troubling. His equations predicted that the universe couldn't be static. It should either be expanding or contracting. But at that time, before Hubble's observations, everyone knew the universe was eternal and unchanging. Einstein faced a choice: trust his equations or trust conventional wisdom. Reluctantly, he modified his equations, adding a term he called the cosmological constant, a kind of anti-gravity that would exactly balance gravity's pull, keeping the universe frozen in place. Imagine a pencil balanced perfectly on its tip, theoretically possible but unimaginably unstable. The slightest perturbation and it falls. That was Einstein's static universe, mathematically feasible but physically absurd. When Hubble showed that the universe was actually expanding, Einstein abandoned the cosmological constant, reportedly calling it his greatest blunder. If he'd trusted his original equations, he could have predicted cosmic expansion before it was observed, one of the greatest missed opportunities in scientific history. But here's the beautiful irony: that blunder would return decades later, transformed, essential to understanding the universe's true behavior. We'll come to that resurrection in time. Feel the weight of your body pulled toward Earth's center by gravity. That same force, multiplied across trillions of galaxies, should be slowing the universe's expansion. Through the mid-20th century, observational cosmologists worked to measure precisely how much the expansion was slowing. The number they sought was called the deceleration parameter, how quickly the universe's expansion rate was decreasing over time. Think of ocean tides. The moon's gravity pulls on Earth's oceans, creating high and low tides twice daily. That same gravitational interaction slowly transfers energy from Earth's rotation to the moon's orbit, causing our day to lengthen by about 2 milliseconds per century. The effect is tiny but inexorable. Cosmologists expected something analogous for the universe: tiny but inexorable deceleration, written in the light from distant galaxies, measurable with precise enough instruments. The challenge was technical. To measure deceleration, you need to observe galaxies at different cosmic epochs and compare how fast they were receding then versus how fast nearby galaxies are receding now. You need cosmic markers that are bright enough to see across billions of light years and well understood enough to use as distance indicators. For decades, such measurements remained frustratingly uncertain. The distances to faraway galaxies were difficult to determine precisely. Small errors in distance translate to large errors in expansion rate. The universe kept its secrets hidden behind observational noise. But technology improved. Telescopes grew larger and more sensitive. Imaging systems transitioned from photographic plates to electronic detectors that captured light far more efficiently. Computer analysis became sophisticated enough to process vast amounts of data. By the 1990s, 2 independent teams of astronomers were ready to measure the universe's deceleration with unprecedented precision. They'd found the perfect cosmic ruler, a specific type of stellar explosion called a Type 1, a supernova. We'll explore those discoveries soon. But first, Let's sit with the expectation, the assumption that guided cosmology for most of the 20th century. Imagine you're watching a friend walk away from you down a long, straight road. At first, they're moving quickly, but gradually, so gradually, you barely notice they slow down. Not because they're tired, but because some invisible force is resisting their motion, draining their momentum. That's what gravity should do to the expanding universe. Every galaxy, pulling on every other galaxy, creating a cosmic drag that saps the expansion's energy. The mathematics of general relativity predicted it. The physics of gravity demanded it. Generations of cosmologists assumed it. And they were wrong. Not wrong about gravity. Gravity does exactly what Einstein said it should do. But wrong about what else might be out there, filling the universe with something other than matter and light, something that doesn't just fail to slow expansion, but actively accelerates it. We're about to discover that the universe is stranger than we imagined. That the space between galaxies isn't passive and empty, but filled with an invisible energy that overwhelms gravity's embrace, pushing everything apart with ever-increasing force. But we're getting ahead of ourselves. Let's walk this path slowly as those astronomers did, following evidence where it leads, even when it leads somewhere impossible. Imagine yourself a fleeting spark, carried by a universe that never pauses. Let's step back from equations and observations for a moment. Let's feel what all this means for us, for consciousness arising on a small planet, looking out into a cosmos that's been expanding for almost 14 billion years. There's something profound and unsettling about cosmic expansion. It means we live in a universe that doesn't return. Time flows in only one direction, from dense to diffuse, from hot to cold, from together to apart. Think of yourself on a raft, floating down a river. The current carries you forward, always forward, past shorelines you'll never see again. You can look back at where you've been, but you can't paddle upstream against time's flow. The universe is that river, and we're all on that raft together, moving away from our cosmic origin, unable to return. Every moment, the space between our galaxy and distant galaxies grows. Right now, as you listen to these words, there are galaxies receding from us so quickly that light leaving them today will never reach us. They're crossing a cosmic horizon, slipping beyond the observable universe's edge, gone forever from our view. Imagine standing on a beach, watching a friend swim away from shore. At first, you can see them clearly waving, smiling, then they're just a dot on the water. Then, even the dot vanishes beyond the curve of the sea. They're still out there, still swimming, but forever beyond your sight. That's happening to galaxies right now. Not because they're moving through space especially quickly, but because space itself is expanding fast enough that light from them can't overcome that expansion to reach us. This cosmic isolation is accelerating. Each passing moment, more galaxies slip beyond our observable horizon. The universe we can see is actually shrinking, even as the universe itself grows larger. Think about what this means for the future of consciousness in the cosmos. If intelligent civilizations arise in those distant galaxies, beings who look up at their night sky and wonder about existence as we do, will never know about them. Our light cones, the regions of space-time we can causally interact with, will never overlap. We're like solitary islands in an infinite ocean, each island drifting farther from all the others, the water between us growing, communication becoming first difficult, then impossible, then not even theoretically conceivable. There's a loneliness to this, a cosmic sadness. The universe is full of potential trillions of galaxies, each with hundreds of billions of stars, many surely with planets, some fraction probably with life, and yet we're fundamentally separated by expansion itself. Or imagine sending a letter to a friend who's moving away from you. You write carefully, pour your heart into the words, send it off. But your friend is traveling so fast, receding so quickly, that the letter, even moving at light speed, never catches up. It chases eternally through empty space, a message never delivered, a connection never made. That's every galaxy beyond our local group, our gravitationally bound neighborhood of a few dozen galaxies. Everything else is receding, and the vast majority will eventually be unreachable, even in principle. But there's beauty in this impermanence too. Every moment becomes precious precisely because it won't return. We exist in this particular cosmic epoch young enough that the universe still has stars, old enough that heavy elements exist to make planets and life possible. We're living in what might be called the universe's summer, warm and bright, before the long autumn begins. Billions of years from now, if humanity's descendants still exist and look up at the night sky, they'll see something very different. The Andromeda Galaxy will have merged with our Milky Way, creating a single enormous elliptical galaxy. But beyond that merged galaxy, they'll see almost nothing, just a handful of other nearby galaxies, all the rest having receded beyond visibility. Future astronomers won't see the cosmic microwave background. It will have redshifted into undetectability. They won't see distant supernovae. They won't see the evidence for the Big Bang or cosmic expansion. Looking at their night sky, they might conclude they live in an island universe, a single galaxy surrounded by infinite empty space. They'd be wrong, but they'd have no way to discover their error. The universe would have expanded beyond the horizon of knowability. This raises a haunting question. What have we already missed? What evidence of the universe's true nature has already redshifted beyond detectability, leaving us in ignorance of cosmic truths we can no longer access? We live in a thin slice of time, between a past too dense and hot to observe directly, and a future too diffuse and empty to reveal the cosmos's full structure. We're witnesses to a particular chapter in the universe's story, able to see some things clearly while others remain forever hidden. Think of watching the stars wheel overhead on a clear night. That sky looks eternal, unchanging, the same constellations ancient humans saw. But even those familiar patterns are temporary. Stars are moving through space, their relative positions slowly shifting. In 100,000 years, the sky will be unrecognizable. The Big Dipper will no longer look like a dipper. Orion will lose his belt. Everything we think of as permanent is actually flowing, changing, carried by time's irreversible current. Feel yourself here, now, in this moment. You're a pattern of atoms forged in stellar cores, arranged temporarily into consciousness, aware of your place in an expanding cosmos. You're a way for the universe to know itself, to reflect on its own nature, to feel wonder at its immensity and mystery. And you're fleeting. We all are. Not just individual humans with our decades-long lifespans, but humanity itself, life itself, stars themselves, galaxies themselves, all temporary patterns in space-time, rising and falling like waves on a cosmic ocean. But here's what strikes me as almost miraculous. Despite this impermanence, despite cosmic expansion carrying everything apart, we can still understand. We can still observe distant galaxies, measure their light, decode their motion. We can reconstruct the universe's history from the Big Bang to the present. We can make predictions about its future. The universe is comprehensible. That's extraordinary. There's no fundamental reason reality should be intelligible to minds evolved to survive on an African savanna. Yet here we are, using those minds to unravel cosmic mysteries 13 billion years in the making. We're the universe looking back at itself, understanding itself, marveling at itself. And we have this privilege, seeing the cosmos in its summer, with stars still burning bright, with evidence of expansion still visible because we exist precisely when and where we do. Hold that feeling of being a temporary witness to cosmic grandeur, a fleeting consciousness in an expanding universe, capable of wonder and understanding despite our brevity. Now, let's return to the science. Let's discover what happens when astronomers pointed their telescopes at distant stellar explosions and found something completely unexpected, something that would transform our understanding of the universe's fate. Picture a cosmic lighthouse, its light whispering that the universe is racing faster. By the mid-1990s, two teams of astronomers were racing to measure the universe's deceleration. The High-Z Supernova Search Team and the Supernova Cosmology Project, each comprising dozens of researchers across multiple institutions, each convinced they would soon pin down precisely how much gravity was slowing cosmic expansion. They had the tools, they had the mathematics, they had the perfect cosmic rulers. Type 1, a supernovae. Imagine a lighthouse on a distant shore. You know how bright the lighthouse bulb is its intrinsic luminosity. By measuring how bright it appears from where you're standing, you can calculate exactly how far away it is. Dimmer appearance means greater distance. It's straightforward geometry, encoded in the inverse square law. Brightness falls off proportional to distance squared. Type 1a supernovae work as cosmic lighthouses. Each one has almost exactly the same intrinsic brightness, bright enough to be seen across billions of light years, and they're well understood enough that astronomers can use them to measure distances with unprecedented precision. These aren't ordinary supernovae stellar explosions that occur when massive stars exhaust their fuel and collapse. Type 1a supernovae are different. They occur in binary star systems where a white dwarf, the dense remnant of a sun-like star, accumulates matter from a companion star until it reaches a critical mass called the Chandrasekhar limit, about 1.4 times the Sun's mass. At that precise threshold, the white dwarf can no longer support itself against gravity. It collapses, and the compression triggers runaway nuclear fusion. The entire star explodes in a matter of seconds, briefly outshining its entire host galaxy, forging heavy elements in the inferno and scattering them across space. Think of a thread stretched tighter and tighter. For a while it holds, bearing the increasing tension. Then suddenly, in an instant, it snaps a catastrophic release of stored energy. That's a Type 1a supernova, a cosmic trigger pulled when matter reaches a precise density threshold. Because these explosions happen at the same mass threshold every time, they produce remarkably consistent light curves graphs showing how brightness changes over time. Peak brightness occurs about 3 weeks after the explosion, then fades gradually over months. Most importantly, because they all explode at the same mass, they all have nearly the same intrinsic luminosity. Cosmologists call them standard candles, objects whose true brightness is known, allowing distance to be calculated from apparent brightness. The two competing teams spent years developing techniques to find these supernovae. It's not easy. Type 1a explosions are relatively rare, maybe 1 or 2 per galaxy per century. You need to monitor thousands of galaxies continuously, looking for new points of light that weren't there before. In the early 1990s, this was tedious work. Astronomers would take images of galaxy fields, wait a few weeks, take images again, and painstakingly compare the images looking for new stars. Like searching for a single changed pixel in 2 nearly identical digital photographs. But by the late 1990s, the process had become more automated. Computerized image subtraction could quickly identify candidates. Rapid follow-up observations with large telescopes could capture detailed spectra, confirming the supernova type and measuring its redshift, how much the universe's expansion had stretched its light during its journey to us. Each supernova became a data point. Its apparent brightness told you its distance. Its redshift told you how much the universe had expanded since the light was emitted. Plot distance against redshift for dozens of supernovae at different cosmic epochs, and you can reconstruct the universe's expansion history. Imagine watching a train move along tracks. If the train is slowing down, each successive kilometer takes longer to travel than the previous kilometer. You can measure this deceleration by timing the train's progress at different positions. That's what these astronomers were doing, timing the universe's expansion at different epochs, expecting to measure its gradual slowing. In 1998, both teams announced their results, and neither team found what they were looking for. Picture the moment in a laboratory when a measurement comes back impossible. The instruments must be wrong. The analysis must have an error. Check everything again. Run different tests. The impossible result persists. The distant supernovae were too dim, not dramatically, just about 25% fainter than expected. But that 25% discrepancy meant something profound. Those supernovae were farther away than they should be if the universe's expansion was slowing down. Think of it this way. Imagine you're watching a speeding train approach in the distance. You calculate how long it should take to reach you based on its current speed, assuming it's gradually slowing down. But when it arrives, it's earlier than predicted. The only explanation, it wasn't slowing down, it was speeding up. That's what the supernova data showed. Distant supernovae, whose light had been traveling for billions of years, were farther away than expected. The space between them and us had grown more than models predicted. Somehow, expansion wasn't slowing, it was accelerating. The universe was speeding up. Adam Rees, Saul Perlmutter, and Brian Schmidt, leaders of the two teams, would later share the 2011 Nobel Prize in Physics for this discovery. But in 1998, they were simply confused and astounded. One researcher described checking his calculations over and over, certain there must be an error. "We spent months," he said, "trying to find what we'd done wrong." Another team member put it simply, "My own reaction was somewhere between amazement and horror." Let this sink in. Everything cosmologists thought they understood about the universe's fate was suddenly radically wrong. Think of walking up a hill, expecting it to get steeper as you climb, only to discover you're actually starting to walk downhill. The terrain beneath your feet has somehow inverted. Or imagine dropping a ball and watching it fall, then slow, then stop and then rise again, accelerating upward against gravity. It violates intuition. violates everything you know about how objects should move. That's how the astronomical community felt in 1998. The universe wasn't just expanding a fact they'd known for 7 decades. It was expanding faster now than it was billions of years ago. The expansion was accelerating. Something was pushing galaxies apart with enough force to overwhelm gravity's attraction. Something permeated all of space, invisible and mysterious, growing stronger or at least more dominant as the universe aged. The observations were solid. Multiple teams, independent analyses, consistent results. The distant supernovae were definitely too faint, definitely too far away. The universe was definitely accelerating. But why? What could possibly drive acceleration? What force could be strong enough to outweigh the gravity of trillions of galaxies? The answer, or at least the name we gave to our ignorance, was dark energy. Think of the universe as a stretched rubber band. For decades, cosmologists thought gravity was pulling the ends together, making it gradually contract. But the supernova observations showed the rubber band was actually stretching, not just maintaining its extension, but actively growing longer, pulled by something science had no explanation for. In the months after the 1998 announcements, cosmologists scrambled to make sense of the data. Some proposed the observations were contaminated by cosmic dust, tiny particles, between galaxies that might dim distant supernovae without invoking acceleration. But careful analysis ruled out dust as the primary explanation. Others suggested the distant supernovae might be intrinsically different from nearby ones. Perhaps stars were slightly different billions of years ago, producing supernovae that don't work as standard candles. But observations of nearby Type 1As showed remarkable consistency across cosmic time. The evidence for acceleration kept getting stronger, not weaker. Picture scientists around the world looking at the same data, running different analyses, checking for every possible error, and arriving at the same impossible conclusion: the universe is accelerating. It's a testament to scientific integrity that the community accepted this bizarre finding relatively quickly. The data was too good, too consistent to dismiss. However uncomfortable, however inexplicable, acceleration was real. And with that acceptance came a flood of new questions. If dark energy exists, this mysterious something causing acceleration, what is it? Where does it come from? Has it always existed? Will it continue forever? We're going to explore those questions soon. But first, let's appreciate what we've just discovered together. We've learned that the universe isn't simply coasting on momentum from the Big Bang, gradually slowing under gravity's brake. It's actively speeding up, expanding faster each passing moment. We've learned that roughly 5 billion years ago, coincidentally around the time our solar system formed, the universe's expansion stopped decelerating and started accelerating. For the first half of cosmic history, gravity dominated, slowing expansion. But then, something else took over. And we've learned that our intuitions about the cosmos, our assumptions about how reality should behave, are incomplete. The universe is stranger, more mysterious, more magnificent than we imagined. Feel the strangeness of it. You're sitting on a planet, in a galaxy, carried by an accelerating expansion of space itself, driven by something invisible and barely understood. You live in a universe that refuses to slow down. And we're just beginning to understand why. Sense an invisible tide pushing galaxies apart in silent defiance. Dark energy. Even the name sounds mysterious, doesn't it? Like something from science fiction, a placeholder for ignorance, an admission that we're grasping in the dark. And that's essentially what it is, a name we've given to whatever's causing the universe's accelerating expansion. We don't know what dark energy is. We don't know where it comes from. We don't fully understand its properties. But we can measure its effects, calculate its density, and model how it shapes the cosmos. Think of feeling wind on your face. You can't see wind air is transparent, but you feel its push, watch it bend grass and rustle leaves, hear it whistle through cracks. You know wind exists by its effects, even though the thing itself is invisible. Dark energy is like that, invisible, permeating everything, known only by its cosmic push. The 1998 supernova discoveries forced cosmologists to confront an unsettling reality. Something fills empty space, and that something has properties unlike any matter or energy we've encountered. It doesn't clump into galaxies or stars. It doesn't emit light. It doesn't interact with normal matter in any way we can detect directly. Instead, it simply pushes, relentlessly, uniformly, everywhere. Imagine you're in a room, and the room is slowly growing larger, not because the walls are moving, they're fixed, but because space itself between every part of the room is expanding, carrying everything gently apart. That's dark energy at work, causing space itself to stretch, increasing the distance between any 2 points that aren't gravitationally bound together. The more space there is, the more dark energy there is, because dark energy has constant density about 6 times 10 to the negative 10th power joules per cubic meter. That sounds like almost nothing, and in any small volume it is. But across cosmic scales, with trillions upon trillions of cubic light-years, that minuscule density adds up to the dominant component of the universe's energy budget. Current measurements, primarily from the Planck satellite's observations of the cosmic microwave background combined with supernova and other data, tell us that dark energy comprises roughly 68% of everything in the universe. Not 68% of matter, 68% of everything. Dark matter, the invisible substance that provides extra gravity to hold galaxies together, makes up about 27%. And ordinary matter, the stuff stars and planets and you are made of, is only about 5%. We live in a universe where 95% of its contents are invisible and mysterious. The cosmos is made primarily of things we don't understand. Think of an iceberg. The part above water, visible, tangible, familiar, is just a fraction of the whole. The vast bulk lies hidden beneath the surface. That's our universe. The visible, ordinary matter is the tip. The dark matter and dark energy are the massive, hidden foundation. But dark energy is even stranger than dark matter. Dark matter at least behaves somewhat intuitively. It has mass, it clusters, it exerts gravitational attraction. Dark energy does the opposite. It causes gravitational repulsion, pushing things apart rather than pulling them together. This brings us back to Einstein's cosmological constant, that blunder he introduced to keep the universe static, then abandoned when Hubble showed expansion was real. Turns out, Einstein's cosmological constant is the simplest explanation for dark energy. In the equations of general relativity, you can add a term called lambda that represents a constant energy density inherent to empty space itself. This energy, doesn't dilute as space expands, unlike matter and radiation, which spread out and become less dense as the universe grows. Imagine stretching a spring. The more you stretch it, the more it pulls back, trying to contract. That's how matter and radiation behave. Spread them out, and their density decreases. But dark energy is like a spring that gets stronger the more you stretch it, or rather, it maintains constant tension no matter how stretched it becomes. Pull space apart, and dark energy doesn't diminish. Each new cubic meter of space contains the same density of dark energy as every other cubic meter. This has a profound consequence. As the universe expands, the total amount of matter stays the same, but its density decreases. But the total amount of dark energy increases because there's more space, and each bit of space contains dark energy. Early in cosmic history, when the universe was small and dense, matter dominated. Gravity from all that concentrated matter was the primary force shaping cosmic evolution. But as expansion continued, matter density decreased while dark energy density remained constant. Eventually, around 5 billion years ago, dark energy became dominant. Think of two teams in a tug-of-war. Initially, one team gravity is much stronger, pulling the rope decisively. But gradually, the gravity team gets tired, while the dark energy team maintains constant strength. At some point, dark energy starts winning, pulling the rope back in its direction. That transition point was about 5 billion years ago. Sense that invisible tide, pushing space apart, overpowering gravity's attraction. But what is dark energy really? Calling it a cosmological constant is mathematical description, not physical explanation. What's the actual substance or field or property of space that makes this happen? Nobody knows for certain, but there are ideas. One possibility is that dark energy is quantum vacuum energy, a consequence of quantum field theory. According to quantum mechanics, empty space isn't truly empty. It seethes with virtual particles, constantly popping in and out of existence, borrowing energy briefly before annihilating. This quantum foam has energy density, which could manifest as the cosmological constant. The problem: when physicists calculate how much vacuum energy there should be based on quantum field theory, they get a number that's about 1 with 120 zeros after it times larger than observed dark energy density. That's not a small discrepancy that's being wrong by 120 orders of magnitude, the worst prediction in the history of physics. Something is deeply misunderstood about either quantum mechanics, general relativity, or how they fit together. This is called the cosmological constant problem, and solving it is one of theoretical physics' great challenges. Think of trying to balance an equation where one side is the number 1 and the other side is 1, followed by 120 zeros. They should equal, but they're incomprehensibly different. Either our calculation is fundamentally flawed, or there's some unknown mechanism that nearly perfectly cancels the huge theoretical vacuum energy, leaving only the tiny observed value. Another possibility: dark energy isn't constant. Maybe it's a dynamical field that changes over time, gradually increasing or decreasing. Physicists call this quintessence, named after the ancient concept of a fifth element beyond earth, water, air, and fire. If dark energy is quintessence, its density might have been different in the past and might change in the future. This would have profound implications for cosmic evolution and the universe's ultimate fate. Or perhaps dark energy isn't a thing at all. Maybe general relativity itself breaks down on cosmic scales, and what we interpret as dark energy is actually a signal that Einstein's equations need modification. Perhaps space behaves differently across billions of light years than our current theories predict. Think of Newtonian gravity, brilliantly successful for 3 centuries, then revealed to be incomplete when Einstein showed that gravity is space-time curvature, not a force. Could general relativity itself be an approximation, accurate in most circumstances, but breaking down at cosmological scales? It's possible, but so far, general relativity passes every test we throw at it. Its predictions match observations with stunning precision, from Mercury's orbit to gravitational waves to black hole shadows. If it's wrong about cosmic expansion, it's wrong in such a subtle, specific way that we haven't yet pinpointed the discrepancy. Feel the mystery. We live in an accelerating universe, driven by something we can measure but not explain. This is one of the beautiful aspects of science, the honesty to say, we don't know. There's no shame in ignorance, only in refusing to acknowledge it. Dark energy is our era's great cosmic puzzle, the question that will define 21st century cosmology. And here's what's remarkable. Despite not knowing what dark energy is, we can still study it. We can measure how it affects expansion at different epochs. We can constrain its properties, ruling out some possibilities and narrowing others. We can build better instruments and design new experiments to probe its nature. Think of astronomers before they understood nuclear fusion. They could still measure stars' properties, track their evolution, map their distribution. They knew stars shone without knowing why. Understanding came later, built on careful observation and theoretical insight. We're in a similar position with dark energy. We see its effects clearly, we can measure them precisely, and gradually, through observation and theory working together, we'll uncover its true nature. Imagine standing in a growing room. You can't see what's pushing the walls outward, can't feel it or touch it, but you measure the wall's motion carefully, map how the space changes, look for patterns in the expansion. Eventually, you understand there's something here, even if invisible, and it's reshaping everything. Dark energy is reshaping everything. It determines the universe's geometry, its fate, the ultimate destiny of every galaxy and star. It's the dominant force in cosmic evolution right now, and will be even more dominant in the future. And we get to explore it. We, conscious beings evolved on a small planet, using instruments and mathematics to probe the deepest mysteries of existence. Feel yourself here, in this moment, in this universe, suffused with invisible energy, accelerating toward an uncertain future. And know that even though we don't have all the answers, we're asking the right questions. We're looking up at the stars with wonder and curiosity, trying to understand why the universe refuses to slow down. Close your eyes and feel the universe's rush, carrying you toward the unknown. Let's step away from equations and observations again. Let's feel what dark energy means, not just intellectually, but viscerally. What does it mean to live in a universe dominated by this mysterious, repulsive force? Imagine you're floating in a boat on a vast river. When you first set out, the current was gentle, almost imperceptible. You could row against it if you wanted, make your way to different parts of the river. But gradually, the current has been growing stronger. Now it pulls you forward with increasing force, and no amount of rowing would let you move upstream. That's dark energy. We're all on that boat, every galaxy, every star, every particle of matter in the cosmos carried by a current that's strengthening, accelerating us toward a future we can observe but not resist. For objects that are gravitationally bound, Earth orbiting the Sun orbiting the Milky Way's center, the Milky Way and Andromeda galaxies approaching each other, dark energy has no effect. Gravity's hold is too strong. The expansion of space doesn't push these structures apart. But for anything not gravitationally bound, for any galaxy beyond our local group, the current is irresistible. Those galaxies are already receding, and they're receding faster every moment. We can watch them, study them, measure their light, but we can never reach them. Think of watching a feather blown by wind across a canyon. You see it clearly, drifting farther and farther, but there's no way to retrieve it. It's gone into a realm you cannot access. That's every distant galaxy, carried by space's expansion faster than light, can bridge the gap. There's a profound loneliness to this. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, is currently about 93 billion light-years in diameter. That's enormous, filled with perhaps 2 trillion galaxies, each with billions or trillions of stars. But the part of the universe we can ever hope to reach, even in principle, even if we could somehow travel at light speed, is much smaller. Most of those 2 trillion galaxies are already beyond the cosmic horizon, receding faster than light. As time passes, that reachable volume shrinks. More galaxies cross the horizon. More potential civilizations, if they exist, slip beyond any possibility of contact. The universe becomes more isolated, more fragmented, more alone. Think of standing on a shore as fog rolls in. Initially, you can see the whole beach, other people walking, waves breaking at different distances. But as fog thickens, your visible world contracts. First, you lose sight of the far end of the beach. Then the middle distance vanishes. Eventually, you can barely see beyond your outstretched hand. The world hasn't changed. People still walk, waves still break, but your observable world has shrunk to almost nothing. Dark energy is that fog, not obscuring vision, but actively carrying things beyond reach. Close your eyes. Feel yourself here, now, on this planet, in this cosmic moment. You're surrounded by galaxies, millions visible with amateur telescopes, billions visible with space observatories. But you're also fundamentally separated from them by expanding space, and that separation is growing. There's something both beautiful and melancholy about this realization. We're participants in a cosmic event, an accelerating expansion that will reshape the universe's appearance over billions of years. Future observers will see a lonelier cosmos than we do. But we're here now, in the era when galaxies still shine in the night sky, when evidence of the Big Bang remains visible, when the universe's history can still be reconstructed. We're privileged witnesses to cosmic grandeur, and we're smart enough to understand what we're seeing. Imagine finding a message in a bottle washed up on a beach. The message describes a distant shore, a place you can never visit but can at least know exists. That's what distant galaxies are, messages from unreachable places telling us the universe is larger and more complex than our neighborhood reveals. Dark energy also shapes the universe's future in profound ways. Right now, the universe is still reasonably hospitable to complexity. Stars shine, planets orbit, chemistry happens, life emerges. Energy flows from hot places to cold places, enabling the organization and complexity we call existence. But as dark energy continues driving acceleration, the universe will change. Billions of years from now, star formation will slow as galaxies exhaust their gas supplies. Eventually, new stars stop forming altogether. The universe enters an era dominated by stellar remnants, white dwarfs, neutron stars, black holes slowly cooling in expanding darkness. Tens of trillions of years from now, even these remnants fade. White dwarfs cool to black dwarfs, cold cinders of dead stars. Black holes evaporate through Hawking radiation. The universe approaches something cosmologists call heat death, a state of maximum entropy where no useful work can be extracted from energy, where complexity unwinds, where even the possibility of interesting events vanishes. Think of an echo in a canyon, strong and clear at first, then gradually fading until it's indistinguishable from silence. That's the universe's far future energy spreading, diluting, until even whispers disappear into stillness. But that's trillions of years away, incomprehensibly far future. We shouldn't mourn endings we won't witness in an epoch so distant it's essentially science fiction. Instead, let's appreciate what we have. A universe still young enough to be interesting, old enough to be understood, right, aged for consciousness to arise and wonder at existence. Feel the river beneath you. Feel space expanding, carrying everything forward on an accelerating tide. You're part of this cosmic flow, not just carried by it, but aware of it, able to contemplate it, to feel wonder and curiosity about where it leads. Imagine you're watching a sunset. You know the sun will set completely, that darkness will come, that the day is ending. But that doesn't diminish the sunset's beauty. In fact, impermanence makes it more precious. You pay attention because it won't last, because this particular arrangement of light and color and cloud exists only now. The universe is that sunset fleeting, temporary, incredibly beautiful precisely because it changes. Stars form and die. Galaxies collide and merge. Space expands and accelerates. Nothing is permanent, but everything is magnificent. And here's something that strikes me as profound. Dark energy's existence means the universe has a kind of inherent creativity. Space isn't passive, it's dynamic, capable of expansion, capable of containing fields and energies we're still discovering. The universe generates complexity, structure, consciousness from simple initial conditions and fundamental laws. And it does so while expanding, accelerating, rushing toward heat, death, making meaning in the face of entropy, creating islands of order in a sea of increasing disorder. We're those islands. Life is an island. Consciousness is an island. And we exist because the universe allows it, because the laws of physics and the properties of space permit complexity to emerge, at least temporarily. Feel gratitude for existence, for consciousness arising in a cosmos that could have been lifeless, for intelligence capable of understanding the very forces that shape reality. For this moment, this awareness, this ability to look at stars and see not just points of light, but distant suns, gravitationally bound collections of plasma undergoing nuclear fusion, part of an expanding cosmic web shaped by invisible dark energy. You're the universe, looking back at itself. And right now, In this cosmic instant, you're feeling the invisible force, dark energy, that determines where everything is going. Hold that feeling. Let it settle into your bones. We're going to continue exploring soon, looking at more evidence, considering implications. But first, just be here. In this expanding cosmos, aware of your place in it. Trace the Big Bang's echoes, whispering that the cosmos won't slow. The 1998 supernova discoveries were revolutionary, but science doesn't rest on single observations. One measurement can be a fluke, a systematic error, an artifact of incomplete understanding. True confirmation comes when multiple independent methods converge on the same answer. Over the past 2 decades, astronomers have developed several different ways to study cosmic expansion and dark energy. And remarkably, they all tell the same story. The universe is accelerating, driven by dark energy that comprises about 70% of everything. Let's explore these different lines of evidence, each one a unique window into the cosmos's fundamental nature. First, the cosmic microwave background, that faint glow of light from 380,000 years after the Big Bang, when the universe first became transparent. Think of this radiation as a snapshot of the infant universe, a baby picture showing structures that would eventually grow into galaxies. But it's more than a picture, it's encoded with information about the universe's composition, geometry, expansion history. Satellites like NASA's Wilkinson Microwave Anisotropy Probe and ESA's Planck have mapped this microwave background with extraordinary precision, measuring temperature variations as small as a few millionths of a degree across the sky. Those tiny variations, spots slightly hotter or cooler than average, aren't random. They're patterns created by sound waves rippling through the early universe's plasma, frozen in place when atoms formed and light broke free. Imagine dropping hundreds of stones into a pond simultaneously. Each creates expanding circular ripples. Where ripples meet, they interfere, sometimes reinforcing each other, sometimes cancelling out, creating a complex pattern of peaks and troughs across the water's surface. Freeze that pattern instantly, and you'd have a map of where each stone fell and how strongly the waves traveled. The cosmic microwave background is that frozen pattern, and cosmologists can analyze it to determine the universe's contents. Different mixtures of ordinary matter, and dark energy produce different patterns of hot and cold spots. By matching observations to theoretical models, scientists can infer how much of each component exists. The Planck satellite's final results, published after analyzing data from 2009 to 2013, confirmed that dark energy comprises about 68.3% of the universe, with dark matter at 26.8% and ordinary matter at 4.9%. These numbers come from analyzing patterns in light that's been traveling for 13.8 billion years, a cosmic accounting of everything that exists. Think about that. We can look at faint static in the microwave sky and extract the universe's recipe, its fundamental composition, written in temperature fluctuations invisible to our eyes but crystal clear to our instruments. The cosmic microwave background also reveals the universe's geometry. Einstein's general relativity allows space itself to be curved not just locally around massive objects, but globally everywhere. A universe with too much matter curves positively, like a sphere's surface. Too little matter produces negative curvature, like a saddle. The right amount gives flat geometry, like an infinite plane. Observations show the universe is remarkably flat, so close to perfect flatness that the measurements can't detect any curvature. This flatness requires a specific total energy density, and the only way to reach that density is by including dark energy. Without dark energy, the universe would be obviously curved, contradicting observations. Think of balancing on a knife's edge. Lean too far one direction and you fall into positive curvature. Lean too far the other way and you tumble into negative curvature. Somehow, the universe balances perfectly, flat as far as we can measure. Dark energy is essential to maintaining that balance. Second line of evidence: baryon acoustic oscillations, BAO for short. Remember those sound waves in the early universe, the ripples that created patterns in the cosmic microwave background? Those same waves left another signature, a preferred distance scale in how galaxies cluster today. When sound waves rippled through the early universe's plasma, they carried matter outward from high-density regions. When atoms formed and the universe became transparent, the sound waves stopped their final position, imprinted a characteristic scale, about 490 million light-years, into how matter was distributed. Billions of years later, gravity turned those matter distributions into galaxies. And the original sound wave scale is still visible. Galaxies are slightly more likely to be found 490 million light-years apart than at other separations. It's a subtle effect, requiring analysis of millions of galaxies to detect, but it's there, a cosmic ruler embedded in the universe's structure. Think of a field of flowers that grew from seeds dropped by wind patterns. Most seeds landed randomly, but there's a subtle regularity, a faint periodicity in their spacing that reflects the wind's rhythm. That's baryon acoustic oscillations, an ancient rhythm preserved in modern galaxy distributions. Astronomers use this ruler to measure cosmic expansion at different epochs. By observing how the 490 million light-year scale appears in galaxy surveys at various distances, various times in cosmic history, they can reconstruct how expansion has changed. Once again, the data requires dark energy and acceleration to make sense. The Sloan Digital Sky Survey and other large galaxy mapping projects have measured baryon acoustic oscillations across billions of years of cosmic history, and every measurement confirms expansion is accelerating. Third evidence: gravitational lensing. Einstein predicted that massive objects bend space, causing light passing nearby to curve. This bending can act like a lens, distorting and magnifying distant galaxies. Sometimes it creates multiple images of the same galaxy, or stretches galaxies into arcs, or brightens them enough to see across cosmic distances. Think of looking through an old glass window with imperfections. Objects on the other side appear warped, stretched, multiplied, not because they've changed, but because the medium you're looking through bends light. Clusters of galaxies do this to light from more distant galaxies behind them. By studying how light is bent, the degree of distortion, the pattern of magnification, astronomers can map the mass distribution in those clusters. This reveals not just visible matter, but dark matter too, since all mass contributes to lensing. But here's where it gets interesting for dark energy. The abundance and distribution of massive galaxy clusters changes over time depending on cosmic expansion. In a universe where expansion is slowing, matter continues clumping into larger structures efficiently. In an accelerating universe, dark energy fights this clumping, preventing as much structure from forming. Surveys counting galaxy clusters at different cosmic epochs find exactly the pattern predicted if dark energy exists and causes acceleration. There are fewer massive clusters than there would be in a decelerating universe. It's as if dark energy started pulling space apart fast enough that gravity couldn't finish assembling the largest structures. Imagine building a tower from blocks while standing on a stretching rubber sheet. Early on, before the sheet stretches much, you can stack blocks relatively easily. But as stretching accelerates, it becomes harder to add more blocks. They're being pulled apart faster than you can place them. That's dark energy interfering with structure formation. Gravitational lensing also provides another way to measure cosmic expansion directly. For certain lens configurations, the light from a background galaxy takes multiple paths around the foreground mass, arriving at different times. If the background galaxy has a variable source like a quasar that brightens and dims, those brightness changes appear in each lensed image at different times, delayed by the different path lengths. By measuring time delays between images and combining this with models of the lens mass distribution, astronomers can calculate the exact distance to the lens and background object. Do this for many lenses at different distances, and you reconstruct the expansion history. Once again, acceleration, dark energy, the same answer from a completely independent method. Feel the convergence of evidence, multiple techniques pointing to the same truth. There's something deeply satisfying about this in science when different approaches based on different physics, requiring different instruments and analyses, all agree. It's not just one surprising result anymore. It's a robust, confirmed feature of reality. The universe is accelerating. Dark energy is real, whatever it ultimately turns out to be. Think of a courtroom where multiple witnesses, who don't know each other, all describe the same event in consistent ways. Each witness sees from a different angle, focuses on different details, but the overall story matches. That's the state of dark energy evidence, multiple independent witnesses to cosmic acceleration. Supernovae say, distant explosions are too faint, implying space has expanded more than expected. The cosmic microwave background says the universe's composition and geometry require dark energy to balance the books. Baryon acoustic oscillations say, the cosmic ruler appears stretched in ways that demand accelerating expansion. Gravitational lensing says, structure formation and light deflection patterns match dark energy predictions. And there are others measurements of how galaxies move within clusters, observations of how dark matter halos grow over time. Analysis of weak gravitational lensing where the distortions are so subtle they can only be detected statistically across millions of galaxies. Every technique confirms, every measurement agrees. We live in an extraordinary time scientifically. Within one generation, cosmology transformed from a field with limited data and large uncertainties to a precision science. We know the universe's age to better than 1% accuracy. We know its composition to a few percent. We can measure expansion history across billions of years. This precision comes from technology, bigger telescopes, better detectors, faster computers, but also from human ingenuity, from scientists developing clever methods to extract information from faint signals, from international collaborations pooling resources and expertise. Think of assembling a jigsaw puzzle. At first, you have scattered pieces, unclear patterns, but gradually, as more pieces fit together, the image emerges. Some pieces confirm what you already suspected. Others surprise you, forcing you to revise your understanding of what the complete picture shows. Dark energy was one of those surprising pieces. It didn't fit expectations. But once placed correctly, it made everything else fall into place, explaining the supernova observations, the cosmic microwave background patterns, the baryon acoustic oscillation measurements, the lensing statistics. The cosmos whispers to us in many voices, through ancient light, through gravitational curvature, through the distribution of galaxies, and all those whispers say the same thing: the universe refuses to slow down. Feel the weight of knowledge, the privilege of living in an era when such deep cosmic truths become accessible to careful observation and analysis. We're understanding the universe at its most fundamental level, seeing patterns in phenomena billions of light years away and billions of years old. And we're just getting started. New instruments are being built, new techniques developed, new observations planned. The study of dark energy continues, seeking to pin down its properties more precisely, to determine whether it's truly constant or subtly changing, to maybe eventually understand what it actually is. Imagine a cosmos stretching forever or tearing apart what's next. We've established that the universe is accelerating, driven by dark energy. But what does this mean for the cosmic future? Where is this acceleration taking us? The answer depends on dark energy's nature, whether it remains constant or changes over time, whether it strengthens or weakens. And here's where speculation meets science, where we can extrapolate current understanding into vast futures we'll never witness. If dark energy remains constant, a true cosmological constant as Einstein formulated, then the universe's future is relatively straightforward, if lonely. Cosmologists call it the Big Freeze, or heat death. Picture a sea stretching endlessly in all directions, its surface absolutely flat and calm. That's the universe's far future, matter spread infinitely thin, every galaxy isolated beyond the horizon of every other galaxy, temperature approaching absolute zero, entropy maximized. Here's how it unfolds. Over the next 100 billion years or so, the last stars finish, forming from remaining gas clouds. Our Milky Way merges with Andromeda, creating one large elliptical galaxy. Most other galaxies recede beyond visibility, their light stretched to undetectability by expansion. After about 1 trillion years, 1,000 times the universe's current age, even the longest-lived stars, tiny red dwarfs burning fuel with miserly efficiency, finally exhaust their nuclear fuel. The era of starlight ends. The universe goes dark, except for rare flashes from matter falling into black holes or colliding stellar remnants. Think of a city at night, lights in windows marking life and activity. Then imagine those lights winking out, one by one, over immense time, until only darkness remains. That's the universe without stars, cold, dark, still. For the next 10 to the 40th power years or more, that's 1 followed by 40 zeros, the universe is dominated by degenerate remnants, white dwarfs, neutron stars, black holes. These slowly cool and evaporate. White dwarfs crystallize into giant cosmic diamonds, then chill to the temperature of their surroundings, effectively vanishing into darkness. Black holes evaporate through Hawking radiation, a quantum mechanical effect where particle-antiparticle pairs at the event horizon sometimes separate, one falling in, one escaping, slowly reducing the black hole's mass. Even supermassive black holes, billions of times the sun's mass, eventually evaporate given enough time. By 10 to the 100th power years, a Google of years, even the largest black holes have evaporated. The universe contains only elementary particles, electrons, positrons, neutrinos, scattered across expanding space, occasionally encountering each other in random collisions that briefly create flashes of radiation before fading back into cold darkness. This is heat death, maximum entropy, minimum organization, no free energy to drive processes or create complexity. Time becomes meaningless because nothing changes in any significant way. The universe exists, but doesn't live. Think of a clock wound down, hands stopped, mechanisms frozen, or a book where every page is blank, all stories told, all words faded. That's the universe's ultimate fate if dark energy remains constant, not ending in dramatic destruction, but fading into perfect, eternal stillness. That's an almost incomprehensibly distant future, so far ahead that our minds can barely grasp the timescales involved. The universe has existed for 13.8 billion years. Heat death lies 10 to the 100th power years ahead, trillions upon trillions upon trillions of times longer than all of cosmic history so far. But there's another possibility, darker and more violent. What if dark energy isn't constant? What if it strengthens over time, accelerating expansion faster and faster until space itself tears apart? This scenario is called the Big Rip. If dark energy density increases, if it's not a cosmological constant, but a dynamical field that grows stronger, then eventually acceleration becomes so extreme that even gravitationally bound structures can't hold together. First, galaxy clusters are pulled apart. Then individual galaxies. Then solar systems. Then planets. Then molecules, atoms, nuclei. Everything rips apart, torn by space, expanding faster than any force can resist. Think of stretching fabric. Normally, the threads hold, you can pull the fabric taut, but it maintains its integrity. But if you keep pulling harder and harder, eventually threads snap, the fabric tears, structural integrity fails catastrophically. In the Big Rip scenario, the end comes relatively quickly once it begins. Perhaps 20 billion years from now, not much longer than the universe's current age expansion, accelerates so much that galaxies start shredding. A few million years later, stars tear loose from galaxies. Months before the final rip, solar systems disintegrate. Days before, planets break apart. Milliseconds before, atomic nuclei split. Finally, space itself might reach a kind of singularity, expanding infinitely fast, tearing even space-time's fabric. The universe ends not in quiet darkness, but in violent destruction, structure unraveling down to the quantum scale. This would be like watching time-lapse footage of decay, but accelerated to impossible speeds. Everything that gravity and electromagnetic forces built over billions of years unmakes in moments. However, current observations suggest dark energy is constant or very nearly so. The Big Rip requires dark energy to increase significantly over time, and we see no evidence of that. It remains a theoretical possibility, but not the most likely outcome. There are other scenarios too, depending on dark energy's exact properties. In some models, dark energy might decrease or even reverse, eventually allowing gravity to dominate again. The universe could stop expanding and begin contracting. leading to the big crunch we mentioned earlier, everything collapsing back into a hot, dense state, perhaps bouncing into a new Big Bang. A cyclic universe, eternally expanding and contracting. Or dark energy might remain constant but with different strength than we measure, leading to variants of the Big Freeze with different timescales and outcomes. The point is, we don't know for certain. We can measure dark energy's current properties, but predicting how it behaves across trillions of years requires understanding what it fundamentally is, and that understanding still eludes us. Think of weather forecasting. We can predict tomorrow's weather relatively well, next week's weather less reliably, next month's weather barely at all. Long-term prediction requires understanding underlying mechanisms, not just extrapolating current conditions. Similarly, predicting the universe's fate requires understanding dark energy's mechanism, its origin, its fundamental nature. Until we have that understanding, we're extrapolating, making educated guesses based on current observations, but acknowledging deep uncertainty about the far future. And speaking of uncertainty, there's a puzzle brewing in modern cosmology, something called the Hubble tension. Remember the Hubble constant, the number describing how fast the universe expands, measured by Hubble in 1929 and refined ever since. It's expressed in kilometers per second per megaparsec, telling you how much additional speed a galaxy gains for every megaparsec, about 3.26 million light-years of distance from us. The problem: different measurement methods give different values for the Hubble constant, and the discrepancy is large enough that it can't be explained by random error. Measurements based on the cosmic microwave background analyzing patterns in that ancient light to determine expansion rate give a value around 67 kilometers per second per megaparsec. But measurements based on direct observations of nearby galaxies and supernovae, the cosmic distance ladder method, give a value around 73 kilometers per second per megaparsec. That's about a 9% difference, which might not sound huge, but it's statistically significant. The two methods disagree at over 5 sigma confidence, meaning there's less than 1 in a million chance this is random fluctuation. Something is genuinely wrong or misunderstood. Think of two thermometers measuring the same room temperature, one reading 70 degrees, the other reading 76 degrees. Both are calibrated, both are precise, but they disagree. Either one is systematically flawed, or the room's temperature genuinely varies in ways you don't expect. The Hubble tension might indicate systematic errors in one or both measurement methods, subtle mistakes, or unaccounted biases that skew results. Cosmologists are working hard to find such errors, but so far both methods appear sound. Or it might indicate new physics, something we don't understand about how the universe expands, how dark energy behaves, how structure forms. Maybe the cosmological constant isn't perfectly constant. Maybe general relativity needs modification. Maybe there are additional components to the universe's energy budget that we haven't accounted for. This is frontier science, an open question with profound implications. Resolving the Hubble tension will either reveal errors in our methods or force us to revise fundamental understanding of cosmic expansion. Think of finding a piece of a jigsaw puzzle that doesn't quite fit anywhere. Either you've picked up a piece from the wrong puzzle, or your understanding of what the complete image should look like is incorrect. Either way, something needs adjusting. Sense the edge of knowledge, the boundary where understanding fades into mystery. Cosmology has made extraordinary progress, but we're far from having all answers. Dark energy remains poorly understood. The Hubble tension remains unresolved. The universe's ultimate fate remains uncertain. And that's exciting. We're living in an era of discovery, when fundamental questions about reality remain open, when new observations might overturn or refine current theories, when curiosity and ingenuity drive us to look deeper into cosmic mysteries. Imagine climbing a mountain. Each ridge you crest reveals another beyond it. You thought you were nearing the summit, but the summit keeps receding, new challenges appearing. That's science. Answering one question often reveals new questions, deeper and more subtle. We've learned the universe is accelerating, but we don't know why. We've measured dark energy's density, but we don't know what it is. We've observed expansion's history, but we disagree on its exact rate. Each answer spawns new mysteries, and that's beautiful. It means reality is richer than our theories, means there's always more to discover, means future generations will have their own revolutionary insights and surprising observations. The universe refuses to slow down, but neither does human curiosity, our drive to understand, our ability to look at distant stars and extract profound truths about existence. Feel yourself at this cosmic moment, understanding so much, ignorant of so much more, privileged to exist in an era when universe reveals its secrets slowly, mysteriously, magnificently. We're almost finished with our journey tonight. Two more reflections remain, one on cosmic isolation, one on consciousness as the universe's way of knowing itself. But first, let the mysteries settle. Let the questions breathe. We don't need all answers tonight. Wonder is enough. Picture Earth as a lonely island, watching stars drift beyond reach. Let's return to something personal, something human. What does accelerating expansion mean for us, not as abstract physics, but as conscious beings trying to understand our place in existence? We are cosmically isolated. That's the first truth to sit with. Earth orbits an ordinary star in the outer regions of an ordinary spiral galaxy. Our nearest stellar neighbor, Proxima Centauri, is 4 light-years away, so distant that light, traveling faster than anything else can, takes more than 4 years to bridge the gap. Our nearest large galaxy, Andromeda, is 2.5 million light-years away. And beyond our local group, the gravitationally bound cluster of galaxies, including the Milky Way, Andromeda, and several dozen smaller companions, everything else is receding, carried by cosmic expansion. Think of living on an island in a vast ocean. You can see other islands on the horizon, but they're unreachably distant. And the ocean is widening, carrying islands farther apart, ensuring you'll never visit them, no matter how much you might wish to. That's our cosmic situation. We're islanders in an expanding universe, fundamentally separated from most of what exists. Now add acceleration to this picture. Not only are distant galaxies moving away, but they're moving away faster over time. The cosmic ocean doesn't just separate islands, it actively widens, ensures growing isolation. Eventually, billions of years from now, observers on Earth, if any remain, will see a sparse night sky. The Milky Way and Andromeda will have merged into a single galaxy. Perhaps a few other local group members will still be visible. But everything else will have receded beyond the cosmic horizon. Their light so redshifted it's undetectable. Their existence provable only through ancient records and theories passed down through generations. Those future observers won't see the rich tapestry of galaxies we see today. They won't observe the cosmic microwave background. They'll have no direct evidence that the universe is larger than their galaxy, no way to discover cosmic expansion, no reason to suspect a Big Bang ever occurred. Think of living in a windowless room. You're told stories about what exists outside sun, sky, stars, other people, but you have no way to verify those stories. You can believe based on testimony and reason, but you lack direct experience, personal confirmation. Future observers will be in that room, cosmologically speaking. The universe's evidence will have expanded away, leaving them in relative ignorance of cosmic truths we can still observe. Feel the privilege of existing now, when the universe still reveals itself, when galaxies still shine in our telescopes, when cosmic history remains accessible to careful observation. But there's another layer to this isolation, even now. Even with all our telescopes and satellites and mathematical sophistication, we're alone in a profound way. If intelligent life exists elsewhere in the universe and the cosmos is so vast that it seems almost certain it does somewhere, we may never know about it. Most galaxies are already too far away for contact, even in principle. Light from civilizations in those galaxies will never reach us before they evolve, change, perhaps go extinct. And for galaxies we can still see, the distances involved make communication impossibly slow. Send a radio signal to a galaxy 1 million light-years away, and if anyone receives it and responds, their reply won't arrive for 2 million years. Conversations are impossible across such spans. Even one-way messages become absurd by the time a reply could arrive. The civilization that sent the original message might be unrecognizably changed or vanished entirely. Think of writing a letter that will take centuries to deliver. By the time it arrives, everyone you knew is gone, the culture has transformed, the language might have evolved beyond mutual comprehension. The letter becomes an archaeological artifact, not communication between living beings. This cosmic loneliness is absolute. We're aware of the universe's vastness, its billions of galaxies, its trillions of stars. We can observe structure, measure expansion, calculate how many worlds might exist. But we cannot reach them, cannot communicate with them, cannot share experiences or knowledge or wonder. We're alone with our awareness, gazing out at an unreachable cosmos. And yet, perhaps this isolation makes existence more precious. If we're the only consciousness we'll ever directly encounter, if Earth is the only world we truly know, then our responsibility to it deepens. We become guardians not just of human civilization, but of consciousness itself, at least the only consciousness we're certain exists. Think of a candle in a vast dark room. You don't know if other candles burn elsewhere in the darkness. You can't see them or reach them. But you can tend your own candle, keep its flame alive, appreciate its light against the surrounding void. That's Earth, a candle of consciousness in cosmic darkness, separated from any other possible flames by expanding space, burning briefly in a universe that exists for eons before and after. There's also the question of our place in time. We exist 13.8 billion years after the Big Bang, early in cosmic history, actually. If the universe continues for trillions of years or more, we're living near the very beginning, in the first chapter of an unimaginably long story. Think of human history recorded civilization spans, maybe 6,000 years. That's nothing compared to the 4 billion years life has existed on Earth, which itself is nothing compared to the universe's age. We're newcomers, infants, barely starting to understand our cosmic context. And we're fleeting. Individual human lives span decades. Civilizations last centuries or millennia. Our species, Homo sapiens, has existed for perhaps 300,000 years. Even if humanity survives for 1,000,000 years, 10 million, a billion, we're still a brief flicker in the universe's timeline. Imagine a time-lapse video of cosmic history compressed into one day. The Big Bang happens at midnight. The first stars form around 3 a.m. Our solar system appears around 4 p.m. Life on Earth begins shortly after. All of human history, from first stone tools to present day, occurs in the last tenth of a second before midnight. We're ephemeral. Our entire existence, from first ancestors to last descendants, will occupy the tiniest sliver of cosmic time. Let this perspective settle. It could feel depressing cosmic isolation, temporal insignificance, inevitable ending. We're alone, fleeting, cosmically inconsequential. But I think there's another way to hold these truths. Yes, we're isolated, but we're also participants in something vast and magnificent. We're the universe becoming aware of itself, conscious patterns arising from unconscious matter and energy, capable of wonder and understanding. Yes, we're fleeting, but we exist. Right now, in this moment, consciousness arises. You're here, reading these words or hearing them, your brain processing information, your mind constructing meaning. That's extraordinary, regardless of how briefly it lasts. Think of a wave on the ocean. It rises, crests, breaks, disappears back into the water. Its individual existence is brief, but it was still a wave, still part of the ocean's movement, still beautiful in its moment. We're those waves, temporary patterns in the universe's flow, arising and disappearing, but real while we exist, capable of appreciating existence while we have it. And here's something that fills me with strange hope. Despite isolation, despite cosmic acceleration carrying galaxies beyond reach, we can still understand. We can observe distant light, decode its messages, reconstruct cosmic history, predict universal fate. We might be alone, but we're not ignorant. We might be fleeting, but we're not meaningless. We're consciousness existing in an accelerating cosmos, aware of our situation, capable of finding beauty in it, capable of creating meaning, even as space expands around us. Feel yourself here on Earth, in the Milky Way, in the local group, in an accelerating universe. Feel the loneliness of cosmic isolation. Feel the impermanence of temporal existence. Feel the wonder of being aware of any of this, of having minds capable of grasping such vast truths. You're the universe watching itself run, your matter and energy temporarily arranged into consciousness. You're fleeting and eternal, simultaneously temporary as an individual, part of an ongoing cosmic process that stretches from Big Bang to heat death and beyond. Hold that paradox. Let it fill you with whatever emotions arise: sadness, wonder, acceptance, curiosity, awe. We have one more reflection ahead, the deepest one. But first, breathe, rest. Let these thoughts settle like snow falling gently onto quiet ground. Feel yourself as the universe's eyes, seeing its endless race through you. We've traveled far tonight, from Hubble's first observations of cosmic expansion, through the discovery of acceleration and dark energy, to reflections on our isolated, fleeting place in an accelerating cosmos. Now, let's explore the deepest question of all. What does it mean that we're here, conscious and aware, able to understand the universe, even as it races away from us? There's something almost miraculous about consciousness arising in the universe. For billions of years, the cosmos existed without awareness, galaxies forming, stars burning, planets coalescing, all of it happening in darkness, witnessed by nothing. Then, on at least one small planet orbiting an ordinary star, chemistry became biology. Simple molecules organized into self-replicating patterns. Those patterns complexified over eons, developing response mechanisms, then nervous systems, then brains, then consciousness. And suddenly, spans hundreds of millions of years, the universe had eyes. Matter had arranged itself into structures capable of observing matter, energy into patterns capable of understanding energy, space into forms capable of contemplating space. We are the universe looking at itself. Think of a mirror in an empty room. The room exists, but its existence is unwitnessed, unappreciated. Then someone enters, looks into the mirror, and sees their reflection. Suddenly, existence becomes aware of itself, capable of self-recognition. That's consciousness in the cosmos, the universe developing the ability to recognize itself, to understand its own nature, to ask questions about its origin and destiny. Carl Sagan expressed this beautifully. We are a way for the cosmos to know itself. Not outside observers studying an external object, but the universe's own capacity for self-awareness, localized in conscious beings scattered across space and time. Every atom in your body was forged in a star's core or in the Big Bang itself. The oxygen you breathe, the carbon in your cells, the calcium in your bones, all stardust, all cosmic material recycled from previous generations of stars. You're not separate from the universe, looking in from outside. You're a temporary arrangement of universal stuff briefly organized into awareness before dispersing back into the cosmic flow. Feel that connection. You're not just in the universe, you are universe, manifesting one particular form among countless others, but fundamentally composed of the same matter and energy as everything else. And consciousness, your subjective experience, your thoughts and sensations and emotions emerges from this arrangement. The universe has organized itself into patterns capable of inner experience, of feeling wonder, of asking why. This raises profound questions that science alone cannot fully answer. How does consciousness arise from unconscious matter? Why should arrangements of atoms produce subjective experience? What is it like to be conscious, not what brain processes occur, but the actual felt quality of awareness itself? These questions sit at the intersection of physics, neuroscience, and philosophy. We can map brain activity, identify neural correlates of consciousness, trace how information flows through cognitive systems. But explaining why any of this produces inner experience, the hard problem of consciousness, remains mysterious. Think of describing color to someone who's never seen. You can explain wavelengths, photoreceptor responses, neural processing, but none of that captures what red looks like, the subjective experience of redness itself. Similarly, we can explain neurons and synapses and brain regions, but explaining why this produces consciousness, why there's something it's like to be you rather than nothing at all, resists reduction to physical processes alone. But whatever consciousness is, however it arises, its existence means the universe has become capable of understanding itself. We can observe distant galaxies, measure cosmic expansion, reconstruct history from Big Bang to predict future scenarios. We're not just passive witnesses. We actively investigate, experiment, theorize, discover. We build telescopes to see farther, accelerators to probe deeper, computers to calculate faster. We develop mathematics to describe reality's structure, physics to explain its dynamics, philosophy to contemplate its meaning. In this sense, consciousness isn't merely the universe observing itself, it's the universe's memory, its capacity to know its own past and anticipate its own future. Think of a book that writes itself, recording its own story as events unfold. That's consciousness in the cosmos, the universe documenting its own existence, creating records of what has been and models of what will be. Every scientific discovery, every observation logged, every theory tested is the universe learning about itself through us. And here's where this connects to our journey tonight, understanding cosmic acceleration, dark energy, the universe's refusal to slow down. These aren't just abstract facts, dry scientific data. They're the universe revealing its nature to itself through conscious observers. We discover acceleration not as external spectators, but as participants, as parts of the cosmos that have developed the capacity to know the whole. When you contemplate dark energy, you're the universe contemplating its own dominant component. When you feel wonder at cosmic expansion, you're space itself marveling at its own stretching. When you sense the loneliness of cosmic isolation, you're matter temporarily organized into awareness, feeling the consequences of universal dynamics. You are not separate from what you study. You are the phenomenon, examining itself, understanding itself, feeling emotions about itself. Think of a wave on the ocean becoming aware it's water, asking where water comes from, how waves form, what happens when they break on shore. The wave isn't separate from the ocean, it is ocean, temporarily manifesting as distinct form, briefly capable of investigating the very substance it's made of. This perspective transforms how we relate to cosmic mysteries. When we admit ignorance about dark energy's nature, we're not just acknowledging limited knowledge, we're the universe encountering its own mystery, puzzling over properties it possesses but doesn't yet understand. When we measure acceleration and feel surprise at the universe speeding up, we're reality itself astonished by its own behavior, discovering truths about its nature that weren't previously apparent. All scientific investigation becomes a form of cosmic introspection, the universe examining itself through conscious subsystems, gradually uncovering its own deeper nature. And consciousness isn't just abstract awareness, it's emotional, aesthetic, moral. We don't just understand that the universe is accelerating. We feel wonder at it, find beauty in it, create art and poetry inspired by it. We're the universe's capacity not just to know, but to appreciate, to find meaning in existence beyond mere physical processes. To value truth, beauty, goodness, love qualities that don't reduce to particle interactions but emerge from conscious experience. Think of starlight. A photon emitted from a distant star travels for millions of years across empty space, unchanged, unconscious, purposeless in itself. Then it enters a telescope, gets focused by mirrors, strikes a detector, generates electrical signals, produces data, gets analyzed by computers, interpreted by human minds, and becomes knowledge. That photon becomes part of consciousness. Its journey culminates in awareness, cosmic information encoded in light, decoded by evolved brains, comprehended by minds that are themselves made of atoms forged in stars. The universe is telling its own story, using light as language, consciousness as comprehension. You are the endpoint of countless such journeys, photons traveling from distant sources, carrying information, entering your eyes, becoming your visual experience, contributing to your understanding of reality. Every time you look at the night sky, you're participating in the universe's ongoing process of self-knowing. Every star you see is the universe showing itself to itself through you. Feel the profundity of this. You're not an accident, not meaningless, not cosmically insignificant despite being fleeting and isolated. You're essential to what the universe is doing, becoming conscious, aware, capable of understanding and appreciation. Without consciousness, the cosmos would exist but go unwitnessed, magnificent but unappreciated, full of pattern and structure but devoid of anyone to notice or care. Your existence matters because you are the universe's capacity to matter to itself. Think of a forest with no one in it. Trees grow, birds sing, sunlight filters through leaves, all happening, all beautiful, but unseen, unheard, unappreciated. Then someone walks into the forest, and suddenly beauty is recognized, sounds are heard, scents are noticed, feelings arise. The forest hasn't changed, but now its existence is witnessed. Now it matters in a new way, not just physically present, but consciously experienced. That's what consciousness does in the universe. It transforms existence from mere occurrence to experienced significance, from blind process to appreciated wonder. And specifically tonight, we've witnessed the universe's refusal to slow down. We've contemplated acceleration, dark energy, cosmic isolation, fleeting existence. We've felt wonder and confusion, curiosity and awe. Those feelings, your feelings, are the universe feeling things about itself. Your curiosity is cosmic curiosity. Your awe is the universe astonished by its own grandeur. When you wonder why expansion accelerates, your space itself puzzling over its own behavior. When you feel small beneath the night sky, your matter temporarily aware of the vastness it's part of. When you seek understanding despite knowing you're fleeting, you're the cosmos valuing knowledge even though all particular knowers are temporary. There's something heroic about this consciousness arising in an indifferent universe, asking questions the universe doesn't naturally answer, seeking meaning in a cosmos that doesn't inherently provide it, finding beauty in physical processes that aren't designed for appreciation. We create significance through awareness. We generate meaning through understanding. We produce value through caring about truth and beauty and existence itself. Think of a spark in darkness. The darkness doesn't create the spark, doesn't sustain it, doesn't care whether it exists. But the spark shines anyway, briefly illuminating its surroundings, creating light where there was none. Consciousness is that spark arising not because the universe intends it, but because physical laws permit organization, complexity, awareness. And once arising, consciousness illuminates everything, making the universe known to itself, appreciated by itself, meaningful to itself. You are that spark. So is everyone you know. Everyone who's ever lived, perhaps beings on other worlds, will never meet. Each conscious entity is the universe sparking into awareness, briefly but brilliantly, contributing to cosmic self-understanding before the spark fades. And collectively, across space and time, these sparks form a kind of distributed consciousness, the universe's total capacity for awareness, spread among countless minds, each knowing a little, together knowing much. As we finish our journey tonight, I want you to hold this perspective. You're not an isolated individual in an alien universe. You're a temporary manifestation of universal process, briefly conscious, participating in the cosmos's ongoing attempt to understand itself. The universe is accelerating, driven by mysterious dark energy, racing toward an uncertain future, and you're aware of this. You can contemplate it, question it, feel emotions about it. That awareness is precious beyond measure. It's the universe's gift to itself, the capacity to know, to feel, to understand, to appreciate. When you lie awake at night, looking up at stars, wondering about existence, that's the universe wondering about itself through you. When you feel awe at cosmic vastness, that's space itself amazed by its own scale. When you seek answers to deep questions, that's reality investigating its own nature. And when eventually your consciousness fades, as all individual consciousness does, you don't really disappear. The atoms that compose you return to the cosmic flow, recycled in the ongoing dance of matter and energy. The patterns that were you dissolve, but the substance remains, available to form new patterns, perhaps new consciousness. You're a wave that rises and falls, but the ocean persists. You're a flame that flickers and dies, but the possibility of fire remains. You're consciousness that emerges and disperses, but the universe continues its process of self-knowing through other minds, other moments. Think of a conversation that spans generations. One person speaks, shares knowledge, then falls silent. But others hear, learn, carry the conversation forward in new voices. The conversation itself continues even as individual speakers change. That's consciousness in the universe, an ongoing cosmic conversation about existence, with countless voices contributing briefly before yielding to new speakers, but the conversation itself persistent, accumulating understanding, building on past insights. Feel yourself here, now, in this moment. You are the universe, aware of itself, contemplating its own expansion and acceleration, marveling at its own mystery. You are stardust that learned to wonder. You are the cosmos's capacity for curiosity. You are space and time temporarily organized into awareness. And right now, tonight, as you've journeyed through these 2 hours exploring why the universe refuses to slow down, you've participated in something profound, the universe understanding itself a little better, knowing itself a little more deeply, appreciating itself a little more fully. Thank you for taking this journey with me. Thank you for lending your consciousness to cosmic contemplation. Thank you for being a spark in the darkness, a way for reality to recognize itself.